which is the research field matter, and particularly dark matter. So it's my pleasure to welcome Felix Kahlhöfer, who is professor at KIT, and he will not only talk about collider physics, but also astrophysics, and how this combines with statistical methods and machine learning. So, if the mic works.
Sure. Does it work?
Yes, it will be turned on. Please, the stage is all yours.
It's great to be here and to invite you to another complete change of topics from law to particle physics. Now, particle physics, of course, has played a pioneering role in the development of AI already 20, 30 years ago, and it still does to some degree, but nowadays we are also kind of trying to stay on top of things. There are so many developments happening in all the different branches of science that very often we try to understand how those can be relevant for us. And I'm going to give you one example of an interesting development that we are quite excited by, which is the idea of simulation-based inference. But before I do that, since there are not a lot of particle physicists in the audience, I should say a few words about what particle physics actually means, what we do. And to first approximation, at least in high-energy particle physics, what we do is we take known particles, things like protons or electrons, and we accelerate them to very, very high energies. And then Einstein's theory of relativity tells us that this energy can be converted into mass. So we can produce new particles with much higher masses than the ones we started with, for example, Higgs bosons, which we are very excited about. Now, the problem is that we don't actually know what is going to happen when we collide particles. At the microscopic level, processes are governed by quantum mechanics, so they are essentially random. And on top of that, the way how detectors react to the particles that we produce also is random. There's noise, there's resolution effects, and so on. So we don't know what's going to happen. And most of the time, what is going to happen is boring, processes that we are not interested in. And the processes that we want to observe are extremely rare, which means, first of all, we have to produce a huge amount of data. We have to run these collisions billions and billions of times before something happens that actually teaches us something fundamental, new about nature. And on top of that, every single collision in itself is incredibly complicated. So this is what's illustrated here in the bottom. When we collide two particles, most of the time we produce a lot of new particles that leave different kinds of traces in our detectors, and we have to make sense of these complicated data sets. And that really means, in a sense, we are doing data science with very complex data sets. Now, the good news is that we do understand in a lot of detail what actually happens when we run these collisions. That means we have Monte Carlo simulations that basically produce data sets that look almost exactly like the real data that we take in our experiments. So we can extract simple information from these simulations, like the number of particles that we produce on average, the energies that these particles have, their direction, how the detector responds to them, and so on. This is what we call low-level observables. This is the most basic information about the underlying events. But this information is too unstructured and too complex to analyze directly. So the name of the game is to condense this information into something more feasible. This is something like a summary statistic. So we combine different low-level observables into something that carries information. It carries information about the distinction between interesting events, what we call signal events, and boring events, so background events. And ideally, it should also carry information about the underlying process. An example is shown here on the right. This is actually the discovery of the Higgs boson at the Large Hadron Collider at CERN. And there what we do is we combine different variables that we measure into a single variable that we call the invariant mass. And you see that the background is a smooth line, the dashed line, and then the signal is this small bump on top of that. And it's a peak at a very specific position, 125 GeV, that tells us about the mass of the Higgs boson. So this summary statistic allows for background signal discrimination and for other statistical tests. So what we would do once we have such a summary statistic is basically your standard statistical analysis. We construct a likelihood function which tells us how likely an experimental outcome is, and then we do hypothesis tests, parameter inference, and so on. And you can already see that in this process there are plenty of opportunities for machine learning. because constructing a summary statistic necessarily means loss of information, right? We're compressing data. And we're compressing data in a very specific way depending on the question that we are asking, depending on what is interesting, what is boring, what we want to learn, and so on. And historically, this is a time-consuming process that requires a lot of experience, some feeling for what might work or what might not work. And of course, nowadays, most of this is automated. So things like, at the most basic level, boosted decision trees or, I don't know, graph neural network classifiers and so on that automate this kind of discrimination and reconstruction processes for us. There are also other strategies like anomaly detection, where we don't make a specific hypothesis regarding the signal, but we just try to look for interesting outliers in our large data sets. But in all of these cases, we're still compressing, we're still losing information. And what we would like to do ideally is to go as close as possible to the underlying information, to the low-level observables, and avoid this loss of information, while still retaining the ability to reconstruct underlying model parameters. And you can't do this in a brute force way. The events are just too complex. We can't construct analytical likelihood functions, and we certainly can't extract distributions from Monte Carlo simulations. We would have to run way too many of them. It becomes completely prohibitive. And this is now where this idea of simulation-based inference comes in. And basically, it's just the idea to make use of the fact that we have tools that can simulate particle physics processes very precisely. So that means we can always generate samples from our likelihood. We can generate experimental outcomes that look like what we would expect the actual experiment to give us. And then we can construct so-called implicit models. So that means we use the simulated data to develop, in a sense, an intuition of how model parameters and observables should be connected. So we start on the very left here with our simulation that takes some model parameters. We get an outcome of the simulation, and then essentially this is passed to a neural network or something like that, together with the model parameters to learn these associations. And then essentially the output of that, or a kind of clever rephrasing of the output, gives us our desired parameter inference. And I just want to give you one slide on the kind of more technical details, because I think they are quite interesting. And the main point here is just that even if we don't realize it, neural networks are very often about likelihoods, even when we don't phrase what we do in terms of likelihoods. And the reason is the following. If we have two different hypotheses that we want to distinguish, so hypothesis 1 and 2, and we simulate samples from both of the hypotheses, and we train a classifier such that it can distinguish hypothesis 1 and hypothesis 2, right? Something that we do all the time in machine learning. Then essentially the Neyman-Pearson lemma of statistics tells us that the optimal classifier internally needs to construct a likelihood ratio. Right? So if we want to minimize the binary cross entropy, then this means that we use essentially a likelihood ratio test. So even if we don't know anything about the individual likelihoods for the two hypotheses, so what is called P1 and P2 here, the neural network still, in order to succeed in its task, constructs the likelihood ratio P1 of x over P2 of x. And this is basically exactly what we then need for our statistical inference. It turns out that we can make this idea more complex. We can introduce additional parameters. And there are some very clever ways how you basically sample simultaneously from parameters and observables, and then a classifier that is trained to discriminate between joint probabilities, so observables with matching model parameters, and the marginal probability, so observables and randomly chosen model parameters. When you train on that task, you learn what is called the likelihood to evidence ratio, which is basically the same thing as the Bayesian posterior for the model parameters. So you perform the training, then you take a measurement, and you evaluate with that measurement your classifier, and you extract the posterior. And you don't have to take the measurement before you even train the classifier. You have what's called amortized training, so essentially any possible outcome will give you a posterior. Now, just to make this a bit more concrete, this is my own research, and I will not tell you what an axion-like particle is, largely because we don't know, but it's a hypothetical particle that would be unstable. So we don't observe it directly, we observe its decay products. And what we've been trying to understand is how, from these decay products, we can reconstruct the fundamental properties of such a particle. So its mass and its lifetime, the kinds of things that we're interested in. And it turns out that we want to take all the information into account that we can, how these particles are produced, where they decay, what they decay into, how we reconstruct them in the detector. And when we do that, we can actually, as you see here in the right, we can get a confined posterior that's very close to the truth level information. But then what we're left with is another problem, which is about the background discrimination. So we can reconstruct model parameters, but we still need to get rid of backgrounds. And this is something that we've been thinking about, and we developed a method that we call the search or the hunt for events with posterior overlap. And the idea is just simply that signal events should always give you the same posterior when you reconstruct them. So because the fundamental parameters are fixed, each event should give you matching posteriors. Whereas noise background events will give you different posteriors every time. So in a sense, the only thing that we have to do is perform some kind of clustering on our reconstructed posteriors. As you can see here on the right, we have 3 overlapping signal events and 2 background events that we have separated from the signal. And this is how we can improve the signal over background ratio in our data sets. Now, just one final word on kind of our ongoing research. The next frontier for doing this is not using classifiers, but using diffusion models. And the idea here is that, in a sense, the Monte Carlo simulations that we run are a bit similar to a diffusion process. We have these particles, and they have interactions, and they shower, they create more particles, they leave some traces in our detectors. And when we do statistical inference, in a sense, we want to do denoising of this data. We want to go back to the ground, the initial process. And this is something that has become a very powerful thing in machine learning, these score-based generative models that can really reverse or denoise these diffusion processes. And we've just started recently with a Helmholtz AI project on this topic called NEEDLE, Neural-Based Diffusion Likelihood-Free Estimations. And the idea here is really to explore what these diffusion models can do in the context of particle physics. So how we can apply them to the huge amounts of data that the Large Hadron Collider produces, and how we can reconstruct properties of the standard model, like the Higgs boson mass, and search for new particles, like dark matter. This is a problem of high-performance computing, of software development, and of course then of actual data analysis. So that's it. Just to summarize, particle physics needs machine learning. I think this is completely clear. And it needs machine learning on many different levels. The kind of conventional classifiers, construction of summary statistics, but in particular, ideas like simulation-based inference and nowadays, things like diffusion models. Thank you very much.
Thank you, Felix. That was very interesting to see also, like, as SBI talks, we had like a couple already at the conference, but not really in the research fields of matter. So I see some people standing up, so please.
Thank you very much for your talk. It was really interesting. So did I understand correctly that you tried to use the neural networks for extracting summary statistic, and in the end you resorted to using just full information?
So I think all of these strategies are being used in parallel. A problem with kind of the summary statistics is that, in a sense, you really need to know what you're looking for, right? You want to have a notion of what your interesting things are that you can label in some way, what your background is. And with simulator-based inference, in a sense, you just run through your entire chain of what you expect your collisions to produce, and then you do inference with that outcome.
What I was wondering about is, like, say, when you do actually extract the summary statistic, did you experiment on the different architectures of neural networks, and can you say something about that?
Yeah, so not me personally, but hundreds of particle physicists basically have that as their main job. this is the only way how we make progress with these large data sets.
So, I mean, but
and
in
there
general...
are so just one thing that I mentioned that is popular are graph neural networks. So,
Okay.
so this idea to extract like edge features and so on.
Okay, thank
that
you.
works quite well for us.
Okay, thank you.
Okay, so one short question from Fabian, and then I think I have to cut it short, sorry.
Try to be short, man. Thanks, Felix. This is really cool. I've been trying to do sort of approximate Bayesian inference as sort of an earlier thing of SBI for sort of our cellular or human whatever models, right? And so it's always been bugging me those summary stats selection. So I think it's a really good idea to go in this direction. You mentioned vertical neural networks and so on. I think the latest one is really cool with diffusion models. Last Europe was mostly about like a big part of them, like every second talk or something like that with flow matching, right? This is sort of the more robust version of many of these aspects. You're considering sort of leveraging, in particular, these type of sort of evolutions of diffusion, I think could potentially help in your inference for that?
Yeah, I mean, as I said in the very beginning, there's, to some degree, we are now kind of trying to catch up or to keep up with all the different developments. So a year or two ago, I would have probably here advertised things like normalizing flows or these invertible neural networks, and now it's diffusion models, right? So, and I guess there are newer things here that some people are working on.
Particular flow matching, I think just
so okay, we should talk.
robust.
I'm not familiar in detail. That sounds exciting.
Great. Thank you, Felix, again.
Thank you very much.
So now we're taking a turn from research field of